Okay, this is Kate Winters, and today I will be solving the startled armadillo problem on problem set number 3 for my video generating assignment. The first thing that we're going to do is go ahead and take down all of the information that was given to us in the problem, all of the givens and variables that we already know the answer to so that we don't get them mixed up. The only information given in the initial prompt is that a startled armadillo leaps upward, rising 0.524 meters in 0.250 seconds. So the first thing I'm going to do is go ahead and say that the height h that he got to was 0.524 meters. We know that. And we're going to go ahead and call this height 1 because later in the problem there's a second height that he reaches, so we're going to call this first one height 1. We're going to say that this is time 1 associated with his first height off of the ground, and he gets to that height in 0.250 seconds, also given to us in the prompt. So that's the information given to us initially, and the first question is that we need to figure out what the initial speed of the armadillo leaving the ground would have been. So in this case, the armadillo, once he leaves the ground, is only being acted upon, or the only acceleration is acceleration due to gravity pulling him back towards the ground. We're going to go ahead and set the positive direction as up and the negative direction as down. So I'm going to go ahead and make a note of that for myself so that I know when he is going up, we're going to associate that with positive signs, and when he is moving down, like the acceleration due to gravity, we're going to associate that with negative signs. We're also going to draw a picture just to make sure that we don't mix anything up. So here's the armadillo. That's his face, and this is the ground. At this point in time, this is time 1. He is, so at time t1, he is at a height of 0.524. And we know that time t1 is 0.25 seconds after initially leaving the ground. So when we're solving for initial speed, we need to find a formula that has initial speed in it, and we also have the information for height, so delta x, and time. So the formula that I chose to use was one of the first formulas for constant acceleration. So delta x equals 1/2 acceleration t squared plus initial velocity times time. That's the base equation. But in order to make it more specific for our context, I'm going to go ahead and rewrite it with either the variables that I've used and defined or other constants and terms that I know apply to this situation. First of all, we're not moving in the x direction, we're moving in the y direction, up and down. So I'm going to go ahead and change this to h1, so the initial height that the armadillo is at time 1. And I'm going to keep 1/2. I know that the acceleration is negative 9.81 because it's the acceleration due to gravity. And we know that at this point in time, it's 0.25 seconds from when he left the ground, so 0.25 squared. And we know that his initial velocity leaving the ground is what we're solving for, so we leave that variable. But I'm going to go ahead and call it initial velocity in the y direction just to make sure that I know that this is not traveling side to side, it's up and down. And again, the time is 0.25. We can go ahead and go in and change this h1 to the numerical value that we know it is, 0.524. And then we only have one variable left in this equation, meaning that we can plug and chug to find that the initial velocity in the y direction is 3.32 meters per second. That's the sig figs from this problem. After finding the initial velocity in the y direction, rounded to the correct number of sig figs, the second question is, what is the speed at this height? So when the armadillo is at a height of 0.524 meters, what is his velocity at that point? So in order to solve this, I'm going to use this second equation that is one of the ones for an object under constant acceleration. So the one I'm going to use in this case is velocity final squared equals velocity initial squared plus 2 times the acceleration times the change in distance. So we're going to do the same thing we did over here where we took the general equation and went ahead and plugged in variables or constants that we knew applied to the situation. So in this case, our final velocity is going to be his velocity when he's at 0.524 meters. So the velocity at time t equals 1. So I'm going to go ahead and call it that. The velocity at t equals 1 second. At t equals 0.25 seconds, but this is called t1 based on how I wrote it over here. So that squared equals the initial velocity squared. So that's the same. That's at t equals 0 seconds plus 2 times, we know it's the acceleration due to gravity, negative 9.81. And delta x, in this case, we know the height that he went. So I'm going to go ahead and say h1, and we'll plug that number in a moment. So now that we have all of this, the only variables in this equation that we don't know is this one. We know his initial velocity, we just solved for it, and we know the height because we were given it in the original problem. So we're going to go ahead and plug and chug. The velocity at t equals 0.25 equals the square root of the initial velocity, which is 3.32, squared minus 9.81 times 2 times h1 is 0.524. Sorry, I'm running out of room. And then when we plug this into the calculator, we get a value of 0.870 when we round it for sig figs. And after solving for the velocity at time equals 0.25 seconds, or time 1, or when the armadillo is at a height of 0.524 meters, we're going to go ahead and move on to the third part of the problem, which asks how much higher does it go. So in order to solve for this, we're actually going to extend the timeline of the problem. So originally our timeline kind of ended at 0.25 seconds. That we went from time t equals 0 to time t equals 0.25. But now we're going to call that t1, or we're going to continue to call that t1 while we define a new variable, t2, to be the time that the armadillo reaches the full height of his jump. So at this point in his motion, he has not reached all the way up yet. He's still moving, meaning that he still has velocity in the upwards direction. So he continues to move up before he stops, where we know that at the top of projectile motion, that is when the velocity equals 0. So we're going to call this point in time t2. The actual number, the number of seconds at this point, isn't necessarily important right now. It's just important that we identify this point in time, this aspect of the armadillo's motion, as t2. So we know that the velocity is 0 at t2. Sorry, that's a little messy. The expo marker is a little too big, but velocity at t2 equals 0 because that's the top of his motion. So at the top of his motion, that's the maximum height that the armadillo will go, meaning that what we're looking for is the difference between this maximum height and where the armadillo is in the middle of our first two problems, or at t1. So what we're solving for is the height at t2 minus the height at t1, because it didn't ask how high does the armadillo go, it asked how much higher from t1. So we're looking for the difference between those. We know how high the armadillo is at t1. That's h1, 0.524 meters. So what we need to solve for is the height that the armadillo, like the maximum height of the armadillo's motion. So in order to solve for this, I used this same general formula. So I'm going to write it down again. Velocity final squared equals velocity initial squared plus 2 times the acceleration times the change in distance. In this case, though, final and initial are going to have new meanings, which is why I write the general form first and then go back in and fill in the constants and the variables that apply in this particular application of that formula. So in this case, final is going to be T2 and initial is going to be T1. So velocity final doesn't mean velocity at T1 anymore, which is what it meant up here. Now velocity final means the velocity at T2. So the velocity at the top of the armadillo's motion squared equals the velocity initial, which we're now going to treat as T1 squared plus 2 times the acceleration, which we know to be the acceleration due to gravity. That has not changed because at every point in the armadillo's motion, he is being acted upon by the force of gravity and is therefore under an acceleration of 9.81 meters per second squared. That times the change in height. In this case, or the change in distance. In this case, because this is motion up and down, we know the change in distance is going to have a vertical component, not a horizontal component. So I'm no longer going to define it with h. I'm going to go ahead and define this as delta h. So because we changed initial to mean T1 and final to mean T2, we can go ahead and say that this variable we're solving for, the difference between the height at T2 and T1, is delta H, which is automatically here. So we're not going to, that's one less step that we'll have to go through. If we had made this the initial time, T equals 0, then we would have needed to say h at T2 minus h at T1. But because we changed this to T1, this is already going to be the difference between those two heights. So one less step that we have to do in the end. At this point, I'm going to go ahead and start plugging in variables. So the velocity at the top of the armadillo's motion. We don't actually know this value. We weren't given it, but because this is projectile motion, we know that when an object is at the top of its motion, its maximum height, its velocity is equal to 0. That's when its velocity changes directions. So we can go ahead and say that that whole side of the equation equals 0. And then we solve for the velocity at time 1, which is the velocity at t equals 0.25. So we know that to be 0.870. And then we square it, and plus 2 times the acceleration due to gravity is negative 9.81. And then what we're solving for is delta H. So at this point, we have an equation with only one variable, meaning we can plug and chug in our calculator to go ahead and solve for the value delta H equals 0.039 meters.